Okay, let's look at some of the other types of momentum questions you get that can be considered a bit more difficult because they might have numbers involved, for example. So this one here, you've been told there's a mass coming in with them. So in this case here, we've got a mass coming in with a mass m, velocity v, and it's hitting a stationary mass there, and it's moving off. And you're being asked to show the relationship here between the velocity coming afterwards and the velocity coming in, and prove that it's actually m over m plus m. So when you're looking at this, you've got to think it's a collision. Where do I start with? It looks really messy and hard to do, but start with the total idea of momentum before as a total is going to equal the total momentum afterwards. Anyway, you want to write it, some people put it as a dash. So looking before, you would normally have done two objects there, m1 v1 plus m2 v2. But in this case here, there is no momentum here for this second part. So all you're really basing it on is the mass of the first object and its velocity, which we've actually got here as m times pi v. So you've already simplified that part there to just mv at the start here. Afterwards, you've got one object stuck together, so you're really looking at a total mass here times by one velocity. So what is the total mass based on? Well, it's actually m plus m now because it's stuck together, times by v dashed. So that represents your velocity afterwards there. Okay, so looking at that here, we just got to get this expression like v dashed over v. So if you want to sort of cross these over, you could bring the v down here and do v dashed over v. And on the other side here, you have the m and you divide by m plus m. So you'll end up with m plus m on the bottom. Okay, so m is on the top, and you get an m plus m on the bottom, which is all you needed to do. So it's actually a lot easier than you think when you first look at the question. So go through the routine of using the conservation law, write down your typical things, substitute what you've got, and try and rearrange for the right question here. So this one actually involves numbers, so it's a bit easier, in fact, for most people to sort of start with. But again, you can do p total before, as beforehand, equals p total afterwards. You could normally write this down as total momentum beforehand is equal to total momentum afterwards as well. It's a vectors there. So let's have a look at this question. An object's exploding, breaking into three pieces. So if it's exploding, we're going to assume it's got a zero momentum here. Should probably say from rest there. And it's going to break into three pieces. So the three pieces will be identified as MAVA, MBVB, because that's what they're using over here in the diagram, plus MCVC. And these could all be dashes there because it's afterwards there. So looking at that, you've actually got the result for A and B, so you could substitute that in as 5 tens of 50 to the left here. Well, it's going west actually according to the question. Piece travels west at 5 meters a second. And a piece travelling south at 3, so the piece going south then is going to be added on, so it's 3 5s of 15 for the momentum going south. And we need to try and find this unknown, and we do know its mass is 8 for C. We do not know its final velocity, and that's what we're trying to find, is it? Find the final velocity of the third piece. Okay, so because it's collisions, you can always guarantee that you're going to be using conservation of momentum in most of the cases. You could work out 50 to the left plus 15 to the down. That would actually help, I suppose. So let's go and do that over here then. So 50 and 15. We need to do that as a vector diagram to find out what is that particular momentum going to be to start with. So I would start probably with there. And if you're going to look at that, you're going to do 50 squared plus 15 squared square root. We get the square root of 2,725, which is 52.2, but we'll go to 52. So based on that, then we've got a 52. We need an angle here now. So theta equals 10 to the minus 1 is opposite over adjacent. So it's 15 over 50, 16.7 degrees. Okay, so looking at that, we actually know what this is here. So what you've got is 0 equals 52 going this way, plus 8 VC dashed. So for this total vector afterwards here, the total momentum to be 0, we need this to be 0. So the only way that can happen is if this 8 VC, this VC dash part, VC, goes in the opposite momentum to this one, so that it cancels. And when you rearrange it, you can see that, because if you go and put the 52 on the other side here, it should be subtracting that then, so it's going to go in the opposite direction. And that's the way the VC dash is going to go. All right, so VC dash should be just 52 over 8. So VC dashed equals 52 over 8, which is 8 sixths of 48, 6.5 meters per second. And it's going to be going that way now with that angle that we had before as 16.7 degrees. Now let's try another one here where there is no numbers again, which seems to be very hard. So you've got an object that's come in it struck another object that's come down from the top here, and then they've stuck together and moved off. Okay, so two identical objects of equal mass move at the same speed collide. They join together and move off as shown below. The angle theta is set. Now the question here was find the angle theta. It's not shown here because it's below the picture. So how do you find the angle theta just from those figures there? So all we do know is we've got two objects to start with. So if you look at this idea of P before is equal to P after as a total, so P total after, the dash again there, you've got two coming in. So you've got a MV going up and an M2 V2 going down, and then afterwards we've got a combined velocity by the look of that times via V dash is one object there. So you could call that 1, 2, I suppose. So M1, V1 here. So M1 is actually M, if we call this M1 here, and it's got a half V for its velocity going that way. So you end up with a half MV going in this direction. Similar thing here, you've got an M times by a half V. So M times by a half V here on that side going down. So you've got a half MV going down. And the V is obviously the same there. And on the other side, you've got a 2m now for the mass, because it's got two masses there put together, and times by a quarter V. And we'll call it the dash there. Although actually we'll leave that as a V, because the V's actually relate to each other. So based on that, you've got 2 times a quarter, you've got a half MV. And that's going off in some direction that way. Okay? We want to know what this is going to be. So there are a few ways you can go from here. I will be tempted to go through and cancel out the stuff that's actually common. So the halves can go, because there's a half all through there. If you divide times by 2 all the way through, they'll go. These m's are the same, so we don't need them really. And what you've got here is a v that way, plus a v down, has to equal a v going like this. In other words, this v plus this v down, and if you subtract this, you're going to get plus v going in this direction, has to equal 0. So you've got 3 vectors here that need to equal 0, and if we try and just draw that then, like that and like that. The only way they can be 0 is if the third vector here that we're unsure about actually comes back in and matches there and comes back to there. Now these have all got the same value, v, v and v. So all those vectors are the same length. The only way they can be the same length is if the angles inside are actually all 60 degrees, because this is an equilateral triangle. And if it's an equilateral triangle, the internal angles here are 60. Now that, if you check that out, then the external angle that must be going on must be 120 degrees. And you can work that out, because if you continue this line through here, if that's 60, this must be 120, because the whole angle here would be 180 in a straight line. So that's a tough one that most people would not answer, because of the fact there's no numbers there. But again, if you try going through, here's the law, what are the sort of things I'm going to dealing with, what letters are involved in my particular example here, can I cancel, can I come up with some sort of a vector diagram based on that? Okay, and that's one way of doing this.